Okay, so good afternoon. I'm going to talk about one of the very hot areas of machine learning these days. And it's called adversarial learning. It will become clear why it is called that if you don't know already. This adversarial learning framework has been developed over the last just few years. And what I'm going to try to do is explain it in a mathematically, statistically principled way. It was invented in kind of an ad hoc way, very much ad hoc way. Hopefully you'll understand it from a very basic mathematical perspective. And it's really quite an interesting thing, which I hope you'll agree with me, because it reconsiders how we do learning. Something that we've been doing for 100 years, learning of models, more than 100 years. And it's been done a certain way, and there's a reason why it's been done that way, but that way may not be the best way. And this adversarial learning is a re-examination of it. So let's assume that our goal is to learn a statistical model, p theta of x. So the data is x, the parameters of our model are theta, and our goal is to learn that model. In other words, to learn theta. And so the way this is almost always done is by choosing the parameters that maximize the expected log likelihood. So this is our model. Q of x is the distribution, the true distribution of the data. So Q of x is the true distribution. We don't know Q of x. We want to approximate Q of x with p theta of x. So what we typically do is maximum likelihood learning. We may add some regularization to this. They're Bayesian constructs, which basically boil down to the same thing. And we've been doing this for 100 years. But people who have done this have always been bothered by aspects of it that didn't work too well, despite the fact we always did it. There were problems. And I'll explain those problems or remind you of those problems. And then we're gonna fix them in a kind of a really cute way. So the situation is I can't actually compute that expectation rigorously because I don't know Q of x. The goal is to approximate Q of x. But let's assume that we get to observe samples xi, I 1 to n, from the world that are drawn from this underlying distribution Q of x. And then what we do is we approximate this expectation in this way. This is the way learning has been done since Fisher, before Fisher. This is the foundation of statistics in many ways, but it's got some problems. And if you've worked with it, you know about these problems. But we never thought we could solve the problems, so we just live with them. Okay, so what's the motivation here? So there are many motivations, but let me just kind of show you one, which will be kind of the emphasis of this talk. So what you're looking at is a bunch of images. So I don't know if you can see this, but this is an image, RGB image. And we could have millions of images. And these images could be radiological images. They could be anything, right? And our goal is to build a statistical model of that data. So these are our data. I don't know the Q of x that is responsible for that data, but I want to try to build a model that approximates it. Okay, this is a very hard problem, and it's actually one that was unsolved up until just a few years ago. And I'll show you how we solved it. Okay, so let's try to understand what this technique that we have been using for 100 years or more, what it actually says about our model. So what I did was I rewrote the maximum likelihood equation. We approximate that expectation with samples, but just for simplicity, I'll write it this way. So what does this model discourage? What does this model not like? What does it discourage from the standpoint of a model p theta x? So let's assume, just for argument's sake, that Q of x, remember, is our true underlying distribution. I don't get to see it. I get to see samples from it. But nevertheless, let's assume that this were it. And let's look at a situation in which p theta of x had this distribution. So this solution will almost never happen with maximum likelihood learning. And the reason is, look at what this says. Here, p theta of x is basically 0, where q of x is not 0. So therefore, log of 0 basically is negative infinity, which is the very antithesis of trying to maximize that likelihood. It's the worst thing that could possibly happen. So this will never occur with maximum likelihood learning. So what does maximum likelihood learning like? It likes a situation like this. So I redrew, and pardon my drawing, but anyway, I redrew the q of x best I could. And then I drew a p theta of x. So now, what does maximum likelihood like? It likes it whenever the model has support over the support of the true distribution. So if you look at p theta of x here, it has support over the support of q of x. I tried to be kind to p theta x, so it kind of captured the distribution reasonably well. But notice what else happens. There's no penalty in this setup, or no significant penalty, if p theta of x has non-zero value or support, where q of x has no support, because the expectation will contribute nothing, because you're multiplying it by q of x, which is 0. And the p theta of x is not 0, so therefore that business of blowing up goes away, or blowing up in the wrong direction goes away. So this is what maximum likelihood encourages, and it seems pretty good in some sense, because it says that the model distribution should have support over the support of the true distribution. It should track it reasonably well. But there's no penalty, or very little penalty, if p theta of x has non-zero value where you're outside the support of q of x. Now, for real data, such like this, images have structure. And they actually live in a very small subset, or manifold, of that very high dimensional space. And so what this says is that this setup is really not going to punish you if you have support where the data doesn't live. And so consequently, it is virtually a certainty, after you work really hard with your maximum likelihood learning, if you actually take your model, which you have learned, and you say this is a model of the world, and you draw samples from it, virtually with certainty, they will not look real. They don't look real at all. So that gives you some indication that our model is not very good. And anybody who has done analysis with maximum likelihood, and you actually just draw from your model, you realize it's complete junk. But we just kind of live with it. All right, so this is what we're going to solve today. So the old setup, so the last, again, from Fisher's day and before Fisher, so hundreds of years, this is the setup. We're going to do something really simple. We're just going to flip the order of the q of x and p theta of x. So what would happen if we just flipped these guys? Now, this is actually nobody's ever done this before, because you can't actually compute this, because I don't know q of x. So the reason we did this was not because we thought it was the most brilliant thing in the world. We did it because we could, because we had a model for p theta and we could compute that expectation. But nevertheless, let's see what could happen if we flip those guys. All right, so now the situation flips. Now I rewrite the equation. This is the new setup. So the q of x is here. Problem is I don't know q of x. But in any case, what is discouraged by this setup is the reverse of what's encouraged by the other method, because what happens is if p theta of x is non-zero where q of x is 0, then this guy blows up. And so consequently, what is encouraged by this model is exactly this setup, that p theta of x will have support over a subset of the support of q of x. So the good news about that is that when you draw x from that model, it will look real because it lives over the support of the real data. The bad news is that you actually don't penalize it too much if it's a subset of q of x. So it'll look real, but it actually may just spit out the same thing every single time. Like it actually would not be significantly discouraged if this thing collapses down to a delta function, right? It would, so the situation is that if you draw from this model, it will look real, but the problem is it may just give you the same image every single time, and this actually happens. And so consequently, you actually may only realize a very small support, a very small subset of what the real data looks like. So let's add some regularization. Let's add something that will encourage it not to collapse down to a delta function. And so what we're going to do is we're going to do the same type of learning setup, but then we're going to add an entropy on p theta of x. And we're going to say, fit the model. So model, fit the data, fit the reality of q of x, but also I want you to be spread out. I want the entropy to be high. And so what happens is that delta function now spreads out, and you kind of get what you want. You basically match q of x, and you're limited to the support of q of x, which means that when you draw from this model, it will look real, and it will also capture the diversity of the true data. Okay? So this looks very good. So now, if you look at this and put those two together, that's the setup. And if we could solve that, good things would happen. But the problem, the reason this has not been done before is because we don't actually know q of x. So we actually can't do this naively. But the key thing is a minor miracle occurred in the last 2 years. And I'm going to show you that. Okay? Okay, so now let's just kind of close this chapter a little bit, just to maybe bring this together. So remember that I said traditional learning does this. This is classical maximum likelihood learning. If I add this term, which is independent of theta, nothing has changed. This is a constant. This is the entropy of q of x. And then if I take this and put this together, what this shows is that traditional learning says minimize the Kullback-Leibler distance between q of x, the underlying true distribution, and p theta of x, our model. This seems like a very good thing to do. We've been doing this for over 100 years. But the problem is the Kullback-Leibler distance is not symmetric, and it matters which direction you go. So now what I'm suggesting as a new setup, so I'm repeating this equation. So the new setup is this, which actually corresponds to minimizing the KL in the opposite direction, with the distributions flipped. So the key thing to notice is that traditional learning corresponds to minimizing the KL. The new learning corresponds to minimizing the KL. The only thing that has happened is we've switched the order. And the good thing about this is that if we do this, we would expect that when we draw from our model, what we synthesize from our model should look real, and it should capture the full diversity of the data. So this is good. But again, nobody did this for the last 100 years. And the reason is that you kind of couldn't, because you don't know q of x. So now this is where the minor miracle will occur. Okay, so let's just assume we could compute that. And let's call it g of x. So how would we do learning if we knew g of x? So we have to compute this expectation. all right, with respect to p theta. This is actually somewhat problematic because we have to optimize theta, and the distribution with which we're computing the expectation is kind of on the outside. So what we're going to do, this is kind of the first, there are going to be two key things that we're going to do to make this work. The first is we're going to assume the form of our statistical model is shown here. So we're going to draw z from some simple distribution, say Gaussian distribution, isotropic Gaussian, or uniform distribution. So P of z is a simple distribution. We then run it through a nonlinear function with parameters theta, and then out comes x. This function, that nonlinear function, will transform the random variables from this simple distribution to whatever distribution we want, x to be. We want it to match Q of x. This is going to be represented by deep neural network. All right, but I'm not going to actually talk too much about that today. But in any case, this is a deep neural network. So trick number one, or idea number one, is we're not going to assume a parametric form for p theta of x. We're going to be completely non-parametric. We draw z from a simple distribution, run it through a nonlinearity. The nice thing that happens, the reason we do this, is that integral, now that expectation becomes tractable because the unknown parameter moves inside of the expectation. So therefore, we can use classical optimization to do this. So now, the final question is, how do we get g of x? All right, so now what we're going to think about is the idea that g of x is a critic. And that's the term people use, critic. So let's assume that we have samples x from the true underlying distribution. These are the samples I see from the world. I don't know Q of x, but I get to see samples. And now this is my actor. The actor's job is to try to act like the real data, synthesize the real data. And so this is a simple distribution, isotropic Gaussian or uniform, something like that. Run it through a nonlinearity, which is a deep neural net. That's our actor. And then the critic, we're going to call g of x. The job of g of x is to decide, if I give it data x, did it come from the actor or did it come from the critic? All right, so the critic's job is to build a classifier with parameters, well, I'll say parameters phi. In other words, the critic is characterized by parameters phi. Its job is to classify between these. The miracle that occurs is that the optimal critic is exactly the log likelihood ratio that we want. All right, you can prove that. Actually, pretty easy to prove. So now the game is pretty clear. So this now is some of the details of the critic. This sigma is a logistic function. So here, this is z is drawn from P of z, and then that z is sent into f theta. This is x. And then sigma g phi is my critic. And then Q of x are data from the true distribution. The goal is to try to distinguish between these. It turns out that the optimal solution is equal to this. So therefore, the learning game reduces to the following. So remember that I said if I knew what g was, this is what I would do to optimize theta. So I'll just do that, assuming I know g. And then to get the g, I'm going to solve this problem. These are data, this and that constitute data from my critic. Sorry, this and this constitute data from my actor. And the x drawn from the true distribution is reality. The classifier is trying to distinguish them. The optimal classifier, which is here, turns out to be that log likelihood ratio. So this is, I think, a minor miracle, because we now can solve a problem that we could never solve before, where we can truly learn a distribution that matches the true data distribution, and we can synthesize data that looks real. So think about, at least from my perspective, what this means. When we talk about learning, to me, to learn means you can think, you can imagine, you can dream. If you can't synthesize, you can't dream. If you have a model and every time you draw from that model it looks like complete garbage, there's no way you can dream. So the idea is see the world, build a model of the world that is realistic in the sense that it can synthesize data, and then you can come up and dream things that you never saw before, but they're actually consistent with reality. Okay, so, so how good does this work? So every image that you see here is synthetic. And so what we're doing here is, so remember, remember that the model was we draw Z from a simple distribution and then we send it through a nonlinear function, out comes the data. So what we're doing here is we're moving in the space of Z. So I know the distribution Z, it's my distribution. So I'm just going to move in the space of Z, and then I'm going to spit out an image for every one of those Z's. And so what we're watching is, as we move along the manifold of the data, we're watching the face transform from this face to that face. Every single picture up there is synthetic, drawn from my model, and of course trained on faces, right? So you could never do this with classical methods. All right, so I thought I had a little more time, but so I'm going to skip a bunch of stuff. So let me show you kind of the last example. I'll show you, this is the last example. So not only can we synthesize images, we can also synthesize text. We can write synthetically, right? So what I'm showing you here is a model using this framework where we simultaneously produce an image and then describe the image. So both are synthetic. So I dream up a picture and then I describe it in text. So if you just look at these, that's from the model. That's also from the model. If you read it, first of all, they seem to make sense, and they're proper idiomatically correct English, right? So this is we think pretty stunning, right? This is why AI and machine learning is so hot today. Every single example that you see here is synthetic. All right, so let me summarize. So I left a few things out, but I captured the essence. So we've derived this thing. It's called a generative adversarial network. So the adversarial, hopefully, is clear. We got an actor, we got a critic. And the actor is going to produce images. The critic is going to distinguish true images from synthesized images, and they're going to fight each other until we stabilize. That's the learning process, is actor, critic, actor, critic. And whenever we get to the point like this, the critic has a very difficult time telling the difference between the two of them. So we've derived this from a very principled statistical framework, I would argue. It turns out that all this is learning where the distributions in the KL are flipped relative to classical learning. The reason we couldn't do it was we didn't have, 100 years ago, to do that critic stuff, you need modern computers to compute, right? But but the thing is, if you read the GAN literature, it's called GAN, it's magical. Magic occurs, but actually it's not magic. It's what I've shown. So this is a natural, so GAN is not a magic. It's a natural consequence of what we call the reverse KL. So the usual KL is what we've been doing for 100 years. So we call reverse KL, which is a way that we estimate that log likelihood ratio. I didn't really talk about this, but we also have shown that the framework that we have with some modifications is exactly the original GAN. I didn't talk about this. If you're interested, we have a paper on this, so just ask me. I'll send it to you. And then we get state-of-the-art performance on this. Right? I think these are pretty stunning. We're excited. These are new results for us. So, so anyway, I'm done. Any questions?